So now we can use this concept regarding electron configuration to determine the total number of valence electrons per element in the periodic table. And valence electrons, by definition, are basically electrons that are involved in chemical reactions. So these are the outermost electrons. So valence electrons are electrons in the outermost principal energy level that are involved in chemical bonding or chemical reactions. And so when it says outermost principal energy level, that would be the highest S&P sublevels or subshells. So subshells and sublevels, they mean the same thing. So how do we determine the number of valence electrons per element? So you have to remember that elements in the same group, okay, so elements in the same group or vertical column have the same number of valence electrons. So for example, group 1 elements will have the same number of valence electrons. Group 2 elements, same thing. Group 3, 4, 5, 6, 7, and 8. So if they all are in the same, if you have two elements that are in the same group, they have the same number of valence electrons. So how do we prove that? So again, if you have, let's say, hydrogen, lithium, and sodium, these three elements will have the same number of valence electrons. Group 2 elements, same number of electrons, valence electrons, and so on. So looking at the first group of elements in the periodic table, we have hydrogen, lithium, and sodium. Let's write out their electron configurations. Okay, so for hydrogen, it's 1s1, right? Because hydrogen has one electron. For lithium, it's 1s2, 2s1. For sodium, it's 1s2, 2s2, 2p6, 3s1. So basically, the definition of valence electron here is the outermost principal energy level. So what that means is it's the highest S&P subshell or sublevels. Okay, so for hydrogen, the highest S&P sublevels would just be the 1s, right? And then you count the number of electrons that's in that 1s sublevel. So because we only have one electron in the 1s, hydrogen must have only one valence electron. And we can do the same thing for lithium. The highest S&P sublevel is the 2s because we don't have a 2p. The 2p is empty. So you have one electron in the 2s, and then same thing for sodium, right? We have 1s2 all the way to 3s1. The 3s1 is the highest S sublevel, and so there's only one electron in that sublevel. So the number of valence electron then is 1 for sodium as well. So we know that a 3s is higher in energy because it's got principal energy level 3 or main energy level 3 versus energy level 2. Okay, so you always go with the highest S&P sublevels. So as a reminder here, the valence electrons are the electrons in the highest S&P subshells or S&P sublevels. So all of the elements in group 1 have one valence electron. So looking at these examples here, the number of valence electrons for the main group elements, so if you guys remember, the main group elements are the group A elements. All elements except for the transition elements are main group elements. So the number of valence electrons for the main group elements basically matches their group number. So group 1 elements will have one valence electron. Group 2 elements will have two valence electrons. Group 3 will have 3 valence electrons. And group 8 elements have 8 valence electrons. And we can look at this example here to kind of prove that concept. So if you have beryllium, for example, and magnesium, they're both in group 2 group 2. They should have a total of 2 valence electrons. So when you look at the highest S&P sublevels, again, the 2p is empty for beryllium and magnesium. And so the highest sublevel is the 2s, and you have 2 electrons in the 2s. And so group 2 elements will have a maximum of 2 valence electrons. And so the main point here in this slide is that the number of valence electrons matches the element's group number, with only one exception, which is helium, because we know that helium is a group 8 element because of the fact that it's a noble gas. But because helium only has 2 electrons, then the maximum number of valence electrons for helium is 2. So the next concept here is regarding core electrons. So if you have valence electrons, the outermost electrons, we also have the core electrons. And these are the electrons that are buried deep within the atom, and they're very difficult to access. It would require a lot of energy to access these core electrons compared to the valence electrons. So by definition, core electrons are all the electrons other than the valence electrons. And these are the electrons that are not involved in chemical reactions or chemical bonding. So here's an example. We have silicon. So silicon, when you look at the periodic table, it's in group 4, right? And so silicon has a total of 4 valence electrons. And silicon has a total of 14 electrons, and 4 of them are valence electrons. So that means that silicon has a total of 10 core electrons. It's basically the remaining number of electrons. So if you have 14 total and 4 of them are valence electrons, then 14 minus 4 equals 10 core electrons. All right, and you always want to remember that for the main group elements, the number of valence electrons matches the element's group number. So that's one way to easily determine how many valence electrons there are for a given element, at least for the main group elements. And then subtract that number of valence electrons from the total number of electrons to get the core electrons. All right, so let's look at a few examples here. How many core electrons are there for each element? So we have carbon, calcium, sulfur, and argon. So carbon, if you look at the periodic table, it's group 4, so it has 4 valence electrons. Calcium is group 2, and so it's got 2 valence electrons. Sulfur is group 6, it's got 6 valence electrons, and then argon is group 8, and so it has 8 valence electrons. Okay, so let's look at them one at a time. So carbon in the periodic table has the atomic number 6, and so it has 6 electrons total. And we determined that 4 of them are valence electrons because it's in group 4. And so 6 minus 4 gives us 2 electrons left. And so that's the number of core electrons. And then for calcium, it has 20 electrons, total of 20 electrons. And it has 2 valence electrons, so we're going to subtract 2 from 20. And so we have 18 electrons left, and those electrons are core electrons. And then sulfur has a total of 16 electrons, and 6 of them are valence electrons because it's in group 6. So 16 minus 6 gives us 10 core electrons. And then the last one here is argon, and it has a total of 18 electrons, and 8 of them are valence electrons, and so it also has 10 core electrons. Okay, so far you've learned 3 different ways on how to write electron configuration. The first one is the normal way, right? The normal technique where you have the Aufbau diagram, where you follow the Aufbau principle. So you distribute the electrons in the orbitals based on increasing energy level. So you have the 1s first, and then the 2s, and then the 2p, followed by 3s, and so on and so forth. The second way to do it is by using the noble gas electron configuration, which is sort of a shortcut, right? It's a shorthand notation in which you use a noble gas as your starting point. So you don't have to actually write out the entire electron configuration. You just pick a preceding noble gas, right? So as your starting point. So you have the noble gas prior or before the actual element. So for example, if you have sodium, in order to write out the noble gas electron configuration, you would pick neon as your starting point, followed by 3s1. The third way is using the orbital diagrams, right? So you learn how to draw orbital diagrams. Basically, it's essentially similar to an electron configuration, except you're using boxes as your orbitals, or so you're using boxes as the orbitals, and then you're using arrows or half arrows to indicate what spin the electron has. So it could be spinning up or spinning down. Now, the last one that I'm going to show you is using orbital blocks in the periodic table, right? So you can just look at a periodic table and then be able to write the electron configuration by simply looking at a periodic table and knowing where the element is in the periodic table. In my opinion, this method is the easiest way to determine an element's electron configuration, because all you have to do is look at a periodic table, and depending on where the element is, you'll be able to write out the electron configuration. You can even use the noble gas electron configuration instead of looking at this diagram shown here on the left. Instead of using that, you can just, again, look at a periodic table. But again, it's up to you. Whichever method you want to use in determining any element's electron configuration. But before you can use this orbital block method, you have to know what these orbital blocks are. And one of the requirements is to look at these blocks in the periodic table. So let's pretend that this is the periodic table here. So we have the transition metals here in the middle, and then we have these main group elements, and then also the lanthanide and actinide elements down here at the bottom of the periodic table. And so what are these orbital blocks exactly? Well, these are orbital blocks. Remember that there are 4 different types of orbitals. You have the s orbital, the p orbital, d orbital, and the f orbitals. Okay, so these orbital blocks are based off of those 4 types of orbitals. And so the first block here on the left is the s block, okay, s orbital block, and then the one in the middle is called the d block because they contain a bunch of d orbitals, and then the one on the right are called the p block, and then the one at the bottom is called the f block. Okay, so you have 4 different orbital blocks: the s, d, sp, d, and f. So the number of columns in each block is equal to the maximum number of electrons that can occupy the particular sublevel of that block. So for example, this S block right here contains 2 columns, right? You have group 1 and group 2. The P block contains a total of 6 columns, and you can count it. You have group 3, group 3A all the way to group 8A, the noble gases. So that's a total of 6 columns. And then when you count the number of columns for the D block, you have a total of 10. And then the F block, you have a total of 14. Okay, you can count that, you can double check it yourself. And so because the S block contains 2 columns, according to this statement here, the number of columns is equal to the maximum number of electrons that can occupy that particular sublevel. And so S contains 2 columns, so that means the maximum number of electrons is 2 electrons for that block. And then for the P block, 6 columns, you have 6 electrons. The D block contains 10 columns, 10 electrons. And the F block contains 14 columns, and so you can have a total of 14 electrons maximum. And it's sort of matches the rule regarding the maximum number of electrons that each of these sublevel can hold, right? So an S sublevel can hold 2 electrons, an F sublevel can hold a maximum of 14. And when you look at a periodic table, let's say this periodic table shown here, you have the row number in the periodic table equal to the number or n value of the highest occupied principal energy level. So basically, if you have row number 1, that means that the highest principal energy level that's occupied is the first energy level. So you have n equals 1 n equals 2 for the row number, for the second row number, n equals 3, 4, 5, and 6, and 7. And so these row numbers, or these n values, are basically the principal energy level. Okay, so let's look at this blank periodic table here again. So we have the S block, the D block, P block, and the F block. And so if we have an element, let's say the first column here, we have hydrogen, right? The highest energy level that it's occupied is the 1s, right? Because this is, again, the S block. And so the row number, the n value, is equivalent to the row number. So for a hydrogen atom, the highest energy level that it's occupied is the 1s. Okay, so if you have the element right below hydrogen, which is lithium, the highest energy level that it's occupied with an electron is the 2s, because lithium is on the second row in the S block. So that would be 2s. And you can do the same for sodium, 3s, and so on and so forth. So if you have beryllium, which is on the second row, S block, the highest energy level that it's occupied is also a 2s, similar to a lithium. Now, once you get into the D block, you subtract 1 from the row number. So that means that if you have scandium right over here, number 21, atomic number 21, scandium, the highest energy level that it's occupied is 3D, right? So scandium is on the fourth row. And so if n equals 4, you subtract 1, it becomes 3, right? So scandium has the 3D as its highest energy level that's occupied. So all the elements on the fourth row in the D block has 3D as their highest energy level. And then once you get back to the P block, the highest energy level that's occupied is equivalent to the row number plus the sublevel, okay, or the P block. So, for example, if we have carbon over here, carbon is on the second row, the highest level would be 2P. Okay, nitrogen, oxygen, fluorine, they're all on the second row, so the highest energy level that's occupied will be a 2P. And then once you hit the F block at the bottom, it becomes n minus 2. So that means that if your row number is 6, then you subtract 2 from 6, it becomes 4. So you have 4F, and then down below it is 5F, because 7 minus 2 is 5. All right, so let's look at an actual periodic table here and look at how we can use that technique to determine the electron configuration of any elements in the periodic table. So let's say, again, I'm just going to summarize it. So we have an S block here, we have a P block on the right, D block in the middle, and an F block at the bottom. And then we also have row numbers. You have row number 1, 2, 3, 4, 5, all the way to 7. And these elements here at the bottom, the lanthanides and the actinides are actually inserted here in this row, and that's why they have the same row number as cesium and barium for the lanthanides, and then the actinides have the same row number as francium and radium. Okay, so now let's say that we're trying to write the electron configuration for the simplest element in the periodic table, hydrogen. Right, so we know that hydrogen has one single electron, and we also know that hydrogen is on the first row in the S block. And so the electron configuration then is simply 1s, and then because it has one electron, we put 1s1. So that's the electron configuration of hydrogen. It's 1s1. And then for helium, we know that helium is right over here, but the reason why helium is on this side in group 8 is because of the fact that helium is a noble gas, and noble gases are very stable, and that's why they group them along with the rest of the noble gases. But in terms of number of electrons, helium should be right over here with the group 2 elements. Okay, and so because helium has 2 electrons, then it would still be on the first row, and within the s block. So the electron configuration for helium is 1s2 because it's got 2 electrons. All right, what about for lithium? So once we get to lithium, that's 2s block, right? So that's 2s and then 2. So that means that that's the highest energy level that's occupied by lithium. So to build up the electron configuration, you would again start off with the 1, right? So you have 1s, 1s2, 2s1 for lithium. So you have to include the preceding electron configuration for lithium. So that would be 1s2 and then 2s1 for lithium. For beryllium, that would be 1s2, 2s2 for beryllium. And then once we get to boron, again, we're starting off with hydrogen again. So that would be 1s2, 2s2, and then this is the p block now, so it would be 2p1. Okay, and then we can do the same thing for carbon. That's 1s2, 2s2, 2p2 because it's on the second column. And then nitrogen would be the same, except it's 2p3, 2p4, 2p5, and then for neon, 2p6. Right? So for neon, it's 1s2, 2s2, 2p6. And then we can just keep going. For sodium, 1s2, 2s2, 2p6, 3s1 for sodium. And then for magnesium, it would be 3s2. And then 3p1, 3p2, p3, p4, 5, and 6. And then 4s1, 4s2. And then once you get to the D block, you have to subtract 1 from the row number, right? And that's why we have n-1 for the D block. So for scandium, that would be 4s2 and then 3d1. So the full electron configuration for scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Okay, and we can do the same thing for titanium all the way to zinc. Okay, and then once you hit the p block, it goes back to np, right? So that would be 3d10 for zinc, and then goes back to 4. So 4p1 for gallium. Okay, and then once if you're dealing with one of these elements that involve the F block, you subtract 2 from the row number. So you can use this information to basically write out any electron configuration for any element in the periodic table. And you can also combine this technique with the noble gas electron configuration. So let's say that I want to write the electron configuration for neon, right, Ne. Or let's say I want to write the electron configuration for aluminum, and I want to use the noble gas electron configuration. So aluminum is right over here on the third row, and I'm going to use the preceding noble gas, the noble gas right before aluminum, which is neon, right? So the elements in the periodic table are arranged based on increasing atomic number. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. So the noble gas before aluminum is neon. And so to write the electron configuration for aluminum using noble gas electron configuration, we have neon and then 3s2, 3p1. Okay, so again, Ne, the symbol of Ne, and then 3s2 and then 3p1 for aluminum. And then we can do the same thing for, let's say, gallium, right? So the preceding noble gas is argon, and this is going to be our starting point. So argon followed by 4s2, 3d10, 4p1. All right, so let's look at a few more examples on the next slide here. So again, by knowing the orbital blocks, the n values, and the position of any element in the periodic table, one can easily write the electron configuration for any element. So again, we have the periodic table here, if that helps you out, or you should also have one on hand. So for practice, using the periodic table and orbital blocks, determine the electron configuration for these elements. So we have these elements here, lithium. All right, so lithium is right over here. So this is the S block, and it's on the second row. So to write the electron configuration for lithium, that would be 1s2. Okay, this is 1s1, 1s2, 2s1. So that's for lithium. 1s2, 2s1. All right, for nitrogen, we have nitrogen right over here, which is on the second row. So again, we're going to start off with 1s2, 2s2, 2p3 for nitrogen. So 1s2, 2s2, 2p3. For magnesium, magnesium is right over here on the third row in the S block. So we have 1s2, 2s2, 2p6, and 3s2 for magnesium. And then iron, we can probably just use noble gas electron configuration because it's all the way down here. We don't want to keep writing all the sublevels. And so we're going to start off with argon, the preceding noble gas. And then we know that iron is on the fourth row and in the D block. So for iron, it would be argon followed by 4s2 and then 3d, 1, 2, 3, 4, 5, 6, 3d6. So argon, 4s2, 3d6. Okay, so basically 4s2, 3d6, this part right here, is the electron configuration for argon. All right, and then we can do the same thing for germanium. Germanium is right over here. So it's also on the fourth row in the P block. So we can use argon as our noble gas. So argon, 4s2, 3d10, and then 4p2. Okay, so basically we have 3d10 and 4p2. So this is the electron configuration right here for, again, argon. And then uranium is all the way down here at the bottom. Wow. So this is row number 7 in the F block. So if we use a noble gas electron configuration, that would be radon right here, Rn. So we're going to use Rn followed by 7s2. And then this is actually the d orbitals right here. So you're going to have, this is the D block. So you're going to write down 6. That would be 6d1. So lanthanum and actinium are actually right over here. So they have a d orbital. Okay, so that would be radon, 7s2, 6d1, and then 5f3. So the arrangement of this part right here, the lanthanide and the actinides, the lanthanum and actinium, these two elements right here are actually inserted over here. Okay, so when you count the total number of elements here, there's actually 15 when there's supposed to be only 14, right? And the reason why is because the IUPAC, the organization that arranged the periodic table, decided to include the lanthanum and actinium along with the rest of these elements here because they have similar physical and chemical properties. All right, but I'm not going to ask you on the test something too massive, right? I'm not going to ask you to write out an electron configuration of one of the heaviest elements in the periodic table. And so just the simple ones. So in the beginning of the lecture regarding electron configurations, we talked about the Aufbau principle, which basically states that sublevels are occupied by electrons in increasing energy level. But some of the transition elements or transition metals, the metals in the middle of the periodic table, don't follow this rule to some extent. And so when you look at chromium, copper, these 4 elements right here, chromium, copper, niobium, and molybdenum, they actually don't follow the Aufbau principle. Okay, so for example, these are the expected electron configuration for these four elements if we follow the Aufbau principle. So you have argon followed by 4s2 and 3d1, right? So 4s2 comes first before 3d1 because 4s is lower in energy than 3d. But in reality, the actual electron configuration is shown on the right over here. So for chromium, for example, it's actually 4s1, 3d5. And the reason behind that is due to the energy level of the 3D sublevel. And remember that you have basically 5 different d orbitals, and so it's more stable to distribute the elements, or it's more stable if you distribute the electrons evenly on the 3D sublevel instead of completely filling up the 4s. All right, same thing with copper, niobium, and molybdenum. So instead of 4s2, 3d9 for copper, it's 4s1, 3d10. So for the next test, for the first test, make sure that you know at least the first two. You have to remember that chromium and copper are the two elements in the periodic table that don't follow the Aufbau principle, that they have a different electron configuration compared to the expected electron configuration.